Hello everyone, I'm Zachary. Today I'm talking about JoinBoost, tree models on databases with only SQL. This is a joint work between Columbia University and Microsoft. So for the background, machine learning in databases is very popular. Major databases vendors like Azure, Google Cloud, and AWS has provided machine learning support for a long time, and their success underlined the effectiveness of machine learning on databases. On the other hand, tree models are the topics for these tabular datasets in databases. So this is the Kaggle survey last year asking people what are the most popular machine learning algorithms you use on a daily basis. Among all these models, tree models like decision tree, random forest, and gradient boosting take the lead. In response, machine learning libraries has developed LightGBM, XGBoost, these specialized libraries for user-friendly API and single-node competitive performance. So you may think that applying tree models to databases is natural and easy. Databases are full of tables, and LightGBM, XGBoost, they are specifically designed for these types of tabular datasets. However, the process may not be that easy, as I will illustrate next. So to illustrate the difficulty, let me start with a simple example. Imagine you are an owner of a bakery chain, and you want to collect these ratings from Google Review or Yelp, and you want to use this precious rating dataset to predict your future ratings for your businesses. So ideally, to do this machine learning task, you want to go to your databases, pick the rating as the target variable Y, and pick up features like cake prices, customer ages, locations, and the weather is the feature X. Then you feed the results to these machine learning libraries like LightGBM and XGBoost, hope that they can magically give you a good models. But the core challenge lies in the impedance between how databases and machine learning structure data sets. So databases usually structure data across many tables. We have the sales table that stores these ratings, but all these features like customer age, cake prices are scattered around these dimensional tables. On the other hand, machine learning just need a single table with both X and Y as input. So to bridge this gap, the current solution here is to write these SQL queries that joins all tables together, materialize the join as single table, and then feed the results into the machine learning libraries. This join, materialization, and export process gives us a lot of challenges. So firstly, it's very laborious. Ideally, you just want to pick a feature from databases for your machine learning task. But in reality, you have to navigate through a complex schema to write these SQL queries. And the common data enterprise database schema can be very complex. So this is a public Galaxy schema from the IMDb datasets. It's called Galaxy schema because the tables are scattered around just like the stars in the galaxy. And imagine having to navigate through such a complex schemas, write the join query to the right, and ensure its correctness. It's quite a tedious work. Secondly, it's actually very slow. So ideally, you want to spend most of our time on this machine learning task and improving the prediction. But in reality, most of our time is actually spent on this database joining queries. So we have did experiments to evaluate the cost of both this join materialization and export cost versus this training time. And surprisingly, this join cost is even more than the training cost. Finally, it imposes a security risk. So you have to move your raw data from your databases to the external LightGBM or XGBoost library. During the process, you expose yourself to these data breaches. Imagine your data has this customer information about addresses and their social security numbers. The resulting legal issue could be a nightmare. So previous machine learning libraries comes with a set of challenges because they move data from these databases to machine learning libraries and do this training on these specialized machine learning systems. But what if we can reverse this process? What if we can translate this machine learning into SQL queries and move this machine learning back to databases? So we introduced JoinBoost. JoinBoost is an open source Python library that trains tree models with only SQL queries. It is open sourced, so you can scan the QR code to get access to the GitHub repository and a code demo. So the idea of JoinBoost is to train these machine learning algorithms into SQL queries then the training process is simplified down to executing SQL queries directly in your databases. And finally, the model parameters are returned as the result of the SQL queries. Notice that throughout this process, the whole training is in databases. We start moving the data outside of the databases. So what exactly is JoinBoost? It is a lightweight Python library that provides a LightGBM and XGBoost-like API, but it plugs directly into your databases for this tree training, like gradient boost, random forest, without using a specialized system. So below is the code snippet of how you want to use JoinBoost, which I will walk through them line by line. So the first step here is to connect JoinBoost to your databases. JoinBoost is highly portable. It can connect to a wide range of databases, including the single-node databases like DuckDB, Postgres, or cloud databases like Azure, Redshift, or BigQuery. And it can even be portable to these data frames like Pandas, R, cuDF, and Dask. The next step here is to map up the join graph. So the core difference between JoinBoost and a specialized machine learning library is that it takes many tables as input in the form of a join graph. So in our examples, we have two nodes, sales and date correspond to two tables. And we build an edge between them corresponding to the join key between them. And notice that we have an ongoing features that are trying to automatically infer this join graph for you without manual specification. And we only require this user input for this join graph when there's ambiguities. And finally, we go to the training phase. As I mentioned before, JoinBoost translates this machine learning algorithm into SQL queries, so the training can be simplified down to executing SQL in databases. And we apply a lot of optimization to speed up this performance. The crux of this is a technique called factorized machine learning, which does these translations over join, but without actually materializing join. This part is more technical, and you can refer the details in the technical reports in our GitHub repository. So how fast is JoinBoost? When data fit into the memory, JoinBoost is 3 times faster than the specialized libraries like LightGBM and XGBoost. So we have evaluated our task of training random forests of 100 trees for database of Science2. The plot has y-axis showing the training time and x-axis showing the number of trees for random forests. Starting with the scikit-learn, which is a very popular choice, but it's also super slow, and we have to stop the training after 30 iterations. Next is LightGBM and XGBoost. They are much faster, but however, they still have a high intercept that becomes its core bottleneck here. And this high intercept is due to this join, materialization, and export process. Finally, JoinBoost, even if JoinBoost is trained on DuckDB, which is a general purpose database, it is 3 times faster than LightGBM and XGBoost. Notice that JoinBoost even finishes training before the join and the materialization completes. And how scalable is JoinBoost? Specialized libraries like LightGBM and XGBoost can use Dask for distributed training, and so we compare them with JoinBoost on Dask sequels. And then the result is shown to the right. So the y-axis is the training time, and the x-axis is the size of the databases. We notice that as we increase the database size, the performance of JoinBoost is almost unaffected due to its scalabilities. When the database size is 40, LightGBM actually runs out of memory, even if it runs on 4 virtual machines with over 100 gigabytes each. On the other hand, JoinBoost is 9 times faster than these specialized machine libraries. Finally, we pushed the envelope further by increasing the database size from 40 gigabytes to 1 terabyte. For these specialized machine learning libraries, they theoretically require you to manage and set up over 100 virtual machines in order to run inside of memory. But for JoinBoost, we can piggyback on the existing databases for these scalabilities. So the plot to the right shows the training time versus the number of nodes in the cloud databases. And you can see that the training time decreases with the number of nodes. And that's it. Thank you very much for listening to the talk. And remember that you can always scan this QR code to try JoinBoost yourself, even on the mobile. Thank you so much.